Next speaker is the Dr. Tsutomu Komuro. He works for the Taisei Corporation, and in 1989 he graduated from the Kyoto University, and after that he working for the Taisei Corporation in division for the design, structure design, and then 2012 he is working for the move to the Taisei Corporation too, but the Advanced Center of Technology. During the stay in the Taisei Corporation, he got a PhD from Kyoto University. The PhD thesis is the compressive performance of the reinforced concrete column using ultra high strength concrete. But his topic today is not only the concrete, but also the high strength material. So please.
Thank you very much for the kind introduction. Thank you, Miki-san. So I was a structural engineer of a construction company, Taisei, in Japan. Now I moved to an R&D center of construction company. So Japanese big company has own research and development institute. That's strange. For American, that's strange, but we have own research center. So my topic is reinforced concrete building using high strength materials in Japan. So I explain the background of using high strength materials in Japan. So since 1980s, the demand for high-rise buildings, especially for residential use in urban areas, has continued to increase because of the increase in the population shift from suburbs to urban areas. Affected by this demand, high-strength materials for RC structures were developed in Japan. So this building, I designed this building about 20 years ago. So a national research project we called New RC were carried out from 1988 to 1993, and this chart shows the target at that time, the concrete strength and longitudinal bars specified yielding strength like that. New RC project had promoted the design and construction of high-rise buildings with high-strength materials. This shows the history of high-strength concrete. Our company, our company Taisei, in 1980s, the maximum strength of concrete is just 36 megapascal. But after a new RC project, the maximum strength of concrete went up, and in 2000, in 2000, so we attained the 100 megapascal concrete here, or here, and also we attained 200 megapascal here, and finally 300 megapascal concrete were achieved. But this is very expensive, 200 or 300. So in Japan, usually these around 100 to 150 is used for a residential building for a lower part of columns. This is very expensive because at this time, so in Japan, big company competed the strength of concrete. Our company and another company competed. Which company is the maximum strength attained? So finally, both two company has a experience of 300 megapascal. So the fight was over. So this is a chart of high strength steel in Japan. So large diameter rebars with the strength of 390 and 490, 590, and SD 685 are used for main rebars here. And PC steel bar and SD 785 is used for lateral reinforcement here. And also, when we use a large diameter rebar, we usually use a mechanical joint. There is a typical two kind of mechanical joint. One is threaded rebar joint. So this rebar is threaded, and this is a section of threaded rebar joint here. And also sleeve joint is here. I think sleeve joint is also the common in United States. But in Japan, we use this mechanical joint use a lot. Next, I would explain a precast system in a building field. Rebar arrangement in a joint is often congested, and high-strength concrete is used for the joint. So in this case, joint parts are precasted. And also to make the connection part cast inside fuel, a joint and beams are integrated into one precast member. This is one precast member, and this picture shows this precasting is about to set here, and this is a hole, this hole, and then we pour cement here, grout here. So next, I will explain application of high-strength materials to a practical project. This is a residential project. The maximum, the story is 43-story residential project, and the maximum strength of concrete is 150. And 150 concrete is used for columns of from first story to third story here, and 130 is used for from 4th story to 8th story, and 100 from 9th story to 13th floor story, and then gradually decrease the strength of concrete. By doing so, the dimension of the column is the same, is a uniform from the bottom to the top in this project. This is the frame planning of this project. These are the residential area. To make the residential area spacious, so the span is wide, and also the depth of inside beam is limited to 800 millimeter, and instead the depth of outside beam is 1,100 millimeter in order to make the frame form stiff. This is a chart of detail of beam column joint. To avoid the congestion of reinforcing, so we use a large diameter rebar with high strength. In this case, we use D38 diameter rebars, and also we use an anchor plate here. And this is outside beam, and this is inside beam here. The depth is limited like this. And also the dimension of column is 900 millimeter by 900 millimeter like this. So next I will explain the seismic design. The performance-based seismic design was conducted using pushover analysis, that is static nonlinear, and dynamic analysis. And 3D frame model was used for pushover analysis, and also lumped mass model is used for dynamic analysis. This chart shows the result of static analysis and dynamic analysis. So the skeleton curve of blue line shows the relation of story drift and story shear force of each story. And then dot shows the maximum response of story drift here. We use the 6 kinds of excitations of earthquake of level 2. Level 2 is the return period is about 500 years. So we check the this value, and this value is less than 0.01. This is a criteria of level 2. So criteria is satisfied. And black one is a recorded excitation, and white note shows the artificial earthquake. So finally, I would like to introduce the recent innovative research and application about seismic performance technology. Generally speaking, if the column is not enough strong as the beam, the joint will be damaged before the strength of frame attains. Here, the strength is almost the same, column and beam. In this case, joint might be damaged like this. To avoid this damage, the column should be well stronger than the beams, but in this case, the dimension of the columns will become larger. So to avoid the damage of beam column joint rationally, the hinge relocation system is developed and induced, where the plastic hinges are designed at the relocated position of the beam. And in a conventional system, the plastic hinge position is the surface at the end of the beam here. But in hinge relocation system, the position of plastic hinge is relocated, shifted this position by using a high strength rebar and also mechanical joint here. This is a concept of hinge relocation system. So we did conduct a structure experiment of hinge relocation system. So as I explained, we use a high strength lever here, and we use a mechanical joint here, and this is the position of the hinge relocated position here. So we observe the hinge here, and cracking is here, but the small cracking was observed in the joint here. So we applied this hinge relocation system to a practical project. This project is now under construction, and the site is Sapporo City in the northern city in Japan. The usage is residential. The stories above the ground is 48, and the total height is 175 meters. The maximum strength of concrete is 100 megapascal. So as I mentioned, the feature is hinge relocation design method, and also separated precast column and beams. So we use a high strength concrete, 100 megapascal is used 11 floor and below, and new developed hinge relocation method is applied for the joint from 5th to 44th floors. And to make the seismic performance better, we put the damping device, lead part, here. Damping device is this steel stud column using a low yield steel in a web, this part, web part. So this chart shows a layout of precast. Red one shows columns, and blue and green one shows beam precast. This is a detail of the beam column joint here. We use a pink one. It shows a high strength bar, SD 590, and we use a mechanical joint here, and a normal bar, which is of which strength is SD 490 here. So this part is a critical section of hinge relocated hinge position. Next, I will explain precast construction. In a conventional precast construction, joint and beams are integrated in one precast segment. So in this case, the lever arrangement and form work is very complicated. So this has a disadvantage, and also the extension of beam lever is large, 1,000 millimeter. So this has a disadvantage in manufacturing and transportation. But in the case of hinge relocation method, columns and beams elements are completely separated, and the extension of lever is small, 340 millimeter like this. So this has advantage in manufacturing and transportation and construction like this. So this is a photo of the construction site, and this is a column, and the extension is very small, and we using a mechanical joint here, pushing to this word, and pour a mortar here. This is a scenery of setting the column using a crane. So summary, recent application of high-strength materials to high-rise buildings in Japan are discussed. In order to make the structural seismic performance higher, hinge relocation system had been developed and applied to a high-rise building in Sapporo. Thank you very much.